So I just want to say that with Micha, that it's really impossible to introduce him because he was very much part of that infrastructure at Courant Institute that motivated all that research that we have been doing. He was the one who discovered that many of the questions in his framework with Jack actually requires extremal combinatorics, requires real algebraic geometry. And in fact, I think that many of those questions that Ricky and Eli worked on wouldn't have come up without Micha's contribution. So I am very happy that he accepted to speak at this late hour, which is for him a late hour, but for most people it is not. So thanks a lot, Micha, for accepting to speak.
Okay, I'm on.
Yeah.
I guess so. So good evening, everybody. Thanks a lot for the organizers for inviting me to talk. It's really an honor to talk in the memory of Eli and Ricky. I prepared some introduction by going through all the photos that I had, and I'd like to share them with you. And then I want to talk about the topic that you see here. Okay, so we already heard a lot of what Eli and Ricky have done. So this slide does not contribute much, but among the two of them, Ricky was a really close friend of mine, and Eli was a colleague that I liked and admired. But going through my photos, I'm sad to say that I didn't find a single one with Eli, so I'll have to show you some with Ricky. So here they are. Ricky at the Rhine, Ricky at the Rhine with me. And this is the picture I like best. It's a group photo at Dutch tool, and Ricky is really the centerpiece of it all. As you can see, and some of you may recognize younger versions of yourself. And two more, a very old, young photo of Ricky with Pankaj and with Boris. Let me go into the topic itself. It does not completely follow the work of Eli and Ricky, but there are some connections, especially in the realm of real algebraic geometry. So what I want to talk is about polynomial partitioning. This is an area I spent a lot of time in the past 12 years. And I want to share with you several recent developments on the algorithmic side of the area. I will mention the algorithmic side of it. I will talk about range searching and some recent concrete applications, as you will see in a minute. With the danger that some of you have not heard or managed to forget what polynomial partitioning is, let me go quickly over it. It's a groundbreaking result introduced by Gut and Katz in 2010. Originally, they used it to solve almost completely the famous distinct distances problem of Erdős. But it turned out that it is a powerful tool that can be used to solve a myriad of combinatorial problems in geometry on distinct distances, incidences, and many other things. But the algorithmic side of it also started to raise, so it slowly started to migrate into computational geometry, and with the question of how does one compute polynomial partitions. And recently there has been enough results to give it a fairly solid foothold. So what is polynomial partitioning? Originally, it started with points. You have a set of n points in d dimensions. You fix some degree d, And you show that they showed that there exists a polynomial f of degree at most d. Such a polynomial, its zero set, z of f, partition space into roughly d to the d connected components. This is Warren theorem, also follow from Milner-Norton. But they showed that each of these components contain at most n over d to the d points. This is, of course, the right number on average, but the strength is that it holds for every cell. And if you use later, very good, extend this result, where now you have a set of n k-dimensional algebraic varieties to some constant degree, lines, spheres, whatever. And again, at degree d, and you show that there exists a polynomial f of degree at most d, so that each of the d to the d cells that is zero set induces in space is intersected by at most n over d to the d minus k varieties of the set. Again, standard results in real algebraic geometry show that this is the right number on average. Like if you add up the number of varieties crossing each cell and divide by the number of cells, this is what you get. But the strength is that this holds in the worst case. For every possible cell, this would be the number of varieties. So this would be a simple rendering of polynomial partitioning in the plane. The blue curve is the zero set, and each cell connect component of the complement. In this example, it contains at most 2 points. Notice that some points may lie on the zero set, and in fact, it is conceivable that all the points lie on the zero set. And this is an issue polynomial partitioning has to struggle with. Here, you have points and lines, and again, you want that each cell should contain a small number of points and be intersected by a small number of lines. It has turned out to be a very powerful tool that its main virtue is that it provides you a divide and conquer mechanism for geometric problems. It competes very favorably and beats, in certain senses, older techniques like cutting and simplicial partitioning and stuff like that. It has some challenges, which I will not go into them, but it really gives you a very powerful new hammer to play with. But once the combinatorial problems are handled, you start to ask yourself about the algorithmic part of it. So you would really like to algorithms that use polynomial partitioning for various things. The simplest would be to take a combinatorial bound and turn it into an algorithmic question. Does there exist an element in the set that you want? Like if you talk about incidences, you can ask problems like Hopkoff problem. Does there exist an incidence between points and curves or surfaces or whatever your objects are? I want to talk about range searching with semi-algebraic ranges, which is a prime application of polynomial partitioning. There are several other applications that I'll mention, including 2 that I want to highlight later in the talk. The problem in constructing a polynomial partitioning is that the existence of such a creature depends on hand sandwich cuts in high dimensions. And there are no known efficient algorithms for doing it. All of them are exponential in the dimension, and that gives you a very bad performance for constructing such a partitioning polynomial. But there has been progress, starting with a relatively old paper by Agarwal, Matushek, and myself, and more recently, several other papers like those you see here have given alternative techniques to construct polynomial partitioning polynomials, typically of constant degree, because when the degree is not a constant, the performance deteriorates quite rapidly, but you can make do with a constant degree. And so this is a major application of polynomial partitioning, range searching with semi-algebraic ranges, which I want to spend some time on. So you're given a set P of n points in d dimensions, and you would like to pre-process it into a data structure so that you can answer range searching queries where the ranges are constant complexity semi-algebraic regions in D dimensions. They can be balls, ellipsoids, they can be anything that you like as long as you can describe it in such a way. And the problems you'd like to solve could be emptiness of detection, like does the query range contain any point, any input point, or report all the points that it contains, or count them, and so on. And the reason why polynomial partitioning plays a role here is that the standard way of doing it is take such a region, take the polynomial partitioning, and observe that the boundary of the region crosses only a small number of cells of the partition, which is again a standard result from algebraic geometry. So, and almost every cell is either fully inside or fully outside the region. And you can handle cells that are fully inside quite easily, and you recurse on the cells that the boundary crosses. So that's why polynomial partitioning is extremely helpful here and gives you the best results that you can get. But in fact, you can extend it to a very general setting where you have any set of objects, let's call them blue, and the query is any other type of object, red, and you want to detect some interaction between the query object and the blue object. And the criterion is that they should satisfy some semi-algebraic predicate of constant complexity pi. And the predicate can be anything. You can ask, does the query intersect the input region or be disjoint from it, contain it or be contained in it, being a distance at least one, and anything else you might think of. You pay a price, which has to do with the number of degrees of freedom that the input and query objects have. So here are a few examples. If you look at the third line, for example, you see that circles in 3 dimensions at 6 degrees of freedom. Degrees of freedom is simply the number of real parameters that you need to represent the object. So for circles 3 dimensions, you need 6, 3 to describe the plane that contains it, and 3 to describe the circle within the plane, and so on. And you can solve the problem in 2 complementary fashions. You can solve it in object space, where you map each input object to a point in t dimensions, because you need t coordinates to specify it. And you map each query to a region, which is the set of all objects B for which that satisfy the predicate pi with the query R. It is a semi-algebraic region of constant complexity, and the recent papers, Agarwal, Matushek, and myself, Matushek and Patakova, give you data structures of nearly linear size. O star simply means that I'm hiding constant, like factors like n to the epsilon and things like that. And the query cost is n to the 1 minus 1 over t. This is remarkable because if the queries were half spaces in t dimension, this is the performance that you would get. So the fact that they are semi-algebraic does not cause the bounds to deteriorate, as long as you have control over the number of the resource t. And then you can solve the problem in query space, where you map each query to a point, now in S dimensions, S is the number of degrees of freedom of the queries, and each input object becomes a region, like a dual to the previous one, if you will, which consists of all the queries that satisfy the predicate with the object B. And then you get a dual version of range searching, which is point and closure query, where you ask, does the query point lies in any of the regions, or report all the regions that contain it, or count their number. In a recent paper, one of those that I mentioned earlier, by Agarwal, Arnov, Ezra, and Zal, gives you a data structure that has the opposite performance of speak. It has large space, n to the s, but the query time is only log. And this is again the best that you can do if you were working with half spaces. And by combining the two approaches, you can trade off of any storage in between and any and suitable query time in between. And this is really a very powerful tool because it tells you that you can solve any type of interactions between objects in any dimension, object of any shape, by a simple uniform mechanism whose efficiency depends on the parameters T and S, but once you have them under control, you get the best solution that people know how to get, also for half spaces. The next talk will give two such examples, or discuss several examples, the talk by Esther Ezra, which I'll skip here, but there are many other applications. The first two do not use range searching, but they are applications of this polynomial partition that I would like to briefly mention. The first is eliminating depth cycles in a set of n lines in 3 dimensions, and later in a set of triangles in 3 dimensions, work by joined with Aronov and later with Aronov and Miller. And it has in fact motivated one of the papers on the algorithmic construction of polynomial partitioning. The other related is to eliminate all lenses in an arrangement of n curves in the plane, which means to cut the curves into pieces, into arcs, so that every pair of arcs intersect at most once. They are pseudo segments. This is joint work with Zal, and again with the algorithmic construction of polynomial partitioning, there is also an algorithm to do it efficiently. What I want to talk about is collinearity testing and so-called 3-pole problems in the algebraic decision tree model, and a related problem of segment concurrency of 3 sets of segments, where at least in 2 of the sets, the segments are disjoint. You see the characters involved in both of these results. Sure. Let me talk about this 3-pole problem. Joint work with Aronov and Esther. The setting is that you have 3 sets ABC, each of n points in the plane, and you have a 6-variate real polynomial of some constant degree f. So it is really a trivariate polynomial in A, B, and C, each of which have 2 degrees of freedom, being a point in the plane. The 3-pole problem asks that was to determine whether f vanishes on a triple ABC in the Cartesian product A times B times C. And if you think about the problem for a minute, you see, excuse me, you see that it can be easily solved in quadratic or near quadratic time, but you want to do better, faster. And you would like to do it in subquadratic time. And if you could do it, wonderful things would happen. In particular, you would get a subquadratic solution to collinearity testing. In the collinearity testing, you again have this reset ABC of points in the plane, and you want to determine whether there exists a line that contains a point from each set. There is a collinear tree. The polynomial for determining whether this is true is the famous left turn, so to speak, determinant, which vanishes when the 3 points are collinear. It is, by the way, it is quadratic in a polynomial in the coordinates. Collinearity testing is the most famous, or maybe the most notorious, 3-sum hard geometric problem. 3-sum is the simplest version of this type of problems, where A, B, and C are sets of real numbers, and the question is whether there is a triple in A times B times C that sum to 0. So the polynomial is just x plus y plus z if you, and the points are 1 dimension. 3-sum is a problem that has been studied for 30 years or so, if not more. And the last several years have witnessed dramatic progress in solving the problem. For a long time, it was strongly believed that 3-sum requires quadratic time to solve. But Gronlund and Petty, and later Kane, Lovett, and Moran, showed that this is not the case, and they gave slightly subquadratic solution in the standard real RAM model, but the latter paper by Kane et al. Gave a nearly linear time in the linear decision tree model, which I'll define in a minute. But all this progress hold because for 3-sum, you use only linear sign tests, linear inequalities. And the collinearity test is quadratic, so you cannot use them. Recent work with by Barba and company have managed to extend 3-pole to 3-sum to the 3-pole situation where the polynomial is general, but the sets are still one-dimensional, and the solution takes n to the 12/7 in the algebraic decision tree model. What is this algebraic decision tree model? It's a model in which you pay only for sign tests of constant degree polynomial in the input data, and every other operations are for free. You pay nothing for them, but they are not allowed to access the coordinates, the real parameters that specify the data. They can only look at the discrete data obtained from the comparisons. And it's a fairly standard model by now. It was designed originally for establishing lower bounds, but now it is used for upper bounds to gain insights into problem structure and so on. The other problem I want to mention, trichromatic segment concurrency by these characters. You have 3 sets again, but now there are sets of segments. 2 of the sets, A and B, the segments are pairwise disjoint. And the question is there a concurrent triple of segments? Is there a segment in A, in B, and C that meet at a common point? You can slightly generalize the problem, get an in-triangle segment intersection where A and B are the same, 2 sets of segments, but C is a set of triangles, arbitrary triangles. And the problem is to determine for every triangle in C, to count for every triangle in C, the number of intersecting pairs in A times B, where the intersection point lies inside delta. For example, the segment concurrency problem is shown on the left, and the in-triangle counting problem is shown on the right. The problem has been studied by Chen recently. He gave slightly subquadratic algorithm in the real RAM model and left a remark with no details that it can also be solved in the algebraic decision tree model. And I'll mention something about it soon. So for 3-pole, we have only partial success, which was not easy to obtain. We can solve it only in the 2-by-1-by-1 case. Namely, one of the set can be a set of arbitrary points in the plane, but the 2 other sets each has to be contained in some curve, algebraic curve of constant degree. And then we can solve it, can determine whether the polynomial vanishes from the Cartesian product in time that is slightly subquadratic, n to the 28/15. The time simply means how many sign tests we perform in the model. And if you have 2 vanishing polynomials, 2 polynomials that you want to vanish simultaneously, then you can solve it in full generality even faster, because the problem is more restricted. So if you have a single complex polynomial, it gives you 2 real polynomials. It's real and imaginary parts, and you can solve the problem in subquadratic time. And you can solve collinearity testing in this 2-by-1-by-1 restricted case. It is still open whether anything can be done about collinearity. Subquadratic can be done about collinearity testing in either model. For segment concurrency, we get a bound of n to the 60/31 in the algebraic decision tree model, and that improves this implicit comment by Chen. what do this problem have to do with polynomial partitioning? My last couple of slides. It's too complicated to explain, but let me run through the toy example of Barba and company, where the sets are one dimension. And let me even assume that the polynomial is of the form C equal FAB, bivariate, not trivariate. Now, to solve the problem, you simply have to take the set of all values FAB, sort them, and then search with every C of C through this sorted list. That, of course, takes quadratic or even slightly superquadratic time. And the idea to make it faster is to break each of A and B into blocks of very small size G, N over G such blocks, and sort the values FAB in each pair of blocks separately. This is total nonsense because you still have N square elements to sort. Breaking them into blocks does not help, but it helps in the algebraic decision tree model, because now the comparisons that you need to perform to carry out this sorting are of FAB and FA prime B prime when A and A prime lie in the same block and B prime lie in the same block. And then there is a famous trick very old trick by Friedman that regards the difference in this particular application, regards the difference FAB minus FA prime B prime as a polynomial in A and A prime indexed by B and B prime. If you work out the details, you have NG points, N over G blocks times G square pairs of points in each block, and NG polynomials. And this is the semi-algebraic range searching problem of finding for each of these polynomials the region where it is positive, say, how many points A prime it contains. So we get down to semi-algebraic range searching. And in fact, this is, in this toy example, we are in the plane because A and A prime are real numbers, so you need two coordinates. And then you get a bound similar to the Semeredi-Trotter bound to the people who know it, that looks like what you see here. It is NG number of points to the 2/3, number of polynomials to the 2/3, which is what you get there. And the sorting still takes quadratic time, but not in the algebraic decision tree model, because once you know all the comparisons, you pay nothing for the actual sorting. And then there is the consideration of searching with each element of C, and it is fairly easy to see that every such element has to search in only N over G pairs of blocks. Don't ask me why, there is no time. But altogether, that means that the cost of searching with the elements of C is roughly N square over G. N elements, N over G blocks to searching, log G time to search in each block. And all you need is to choose G's that balances the two expressions above and below, and that gives you the N to the 12/7, which is what they got. In order to do it for planar points, that you have to work much harder, and in fact, not fully successfully, because the main bottleneck is to make sure that every element of C has to search with only a few pairs of blocks, and that's not easy. And we don't know how to do it in general, but we know how to do it for the 2x1x1 tricks case, and on and on and on. And I didn't say anything about the concurrency problem, but my time is up. And thanks again for inviting me, and may Eli and Ricky rest in peace and be remembered by us for a very long time. Thank you.